Good morning, guys. Now let's see about operating system concept. Third unit of operating system is a process synchronizations. This means contains background of process synchronization, critical section problem, synchronization hardware, mutex logs, semaphores usage, semaphores implementation, monitors usage, dynamic crossover solution using monitor, implementation of monitor using semaphores. Let's see it one by one. Background in process synchronizations. On the basis of synchronization, process are categorized as one of the following two types: independent process and a cooperative process. First one, independent process. Execution of one process does not affect the execution of other process. Next one, cooperative process. Execution of one process affects the execution of other process. A process synchronization problem arises in the case of cooperative process also because resources are shared in cooperative process. Next one, critical section problem. Critical section problem is a code segment that can be accessed by only one process at a time. Critical section contains shared variables which need to be synchronized to maintain consistency data variables. In the entry section, the process request for entry in the critical section. Any solution to the critical section problems must satisfy three requirements: mutual execution, so mutual exclusion, progress, and bounded waiting. First one, mutual exclusion. If a process is executing in its critical section, then no other process is allowed to execute in the critical section. Progress. If no process is executing in the critical section and other process are waiting outside the critical section, then only those process that are not executing in their reminder section can participate in deciding which will enter in the critical section next. And, and the selection cannot be postponed indefinitely. Next, bounded waiting. A bound must exist on the number of times that other process are allowed to enter the critical sections after a process has made a request to enter its critical section and before that request is granted. Next one, synchronization hardware. Process synchronization refers to coordinating the execution of process so that no two processes can have access the same shared data and resources. A problem occurs when two processes are running simultaneously share the same data or variable. There are three hardware approaches to solve process synchronization problems. First one, swap, test and set, unlock and lock. First one, test and set. In test and set, the shared variable is a lock that is initialized to false. The algorithm returns whatever value is set to it and sets the locks to true. Mutual exclusion is ensured here as till the lock is set to true, other process will not be able to enter and the loop continues. However, the one process is completed, any other process can go in, so no queue is maintained. Next one, swap. In this algorithm, instead of directly setting the lock to true, the key is first set to true and then swapped with the lock. Similar to test and set when there are no process in the critical section, the lock turns to false and allows other process to enter. Hence, mutual exclusion and the progress are ensured but the bound waiting is not ensured for the very same reasons. Next one, lock and unlock. Uh, in addition, to test and set, this algorithm uses waiting to check if there are any process in the wait. The process are set in the ready queue with respect to the critical section. Unlike the previous algorithm, it does not set the lock to false and checks the ready queue or any waiting process. If there are no process waiting in the ready queue, the lock is then set to false and any process can error. Next one, mutex locks. Matrix is mutual expression object that synchronizes access to resources. It is created with a unique name at the start of a program. The mutex locking mechanism ensures only one thread can acquire the mutex and enter the critical sections. This thread only release the mutex when it exists in the critical sections. Now thread wait and go to the mutex and wait and go to thread release shared resource release thread. This is the flow of thread. It is a special type of binary semaphore used for controlling access to the shared resource. It includes a priority inheritance mechanism to avoid extended priority inversion problem. It allows current higher priority task to be kept in the blocked state for the shortest time possible. However, priority inheritance does not uh, correct priority inversion, but only minimize its effect. Advantage of mutex. Mutex is just simple locks obtained before entering its critical sections and then releasing it. Second one, since only one thread is in its critical section at any given time, there are no race conditions and the data always remain consistent. Next one, semaphore. Semaphore is simply a variable that is non-negative and shared between thread. A semaphore is a shine signaling mechanism, and another thread can signal a thread that is waiting on a semaphore. This shows the semaphore flow. Thread the data move to the wait state and to semaphore, and then put the wait and thread and release thread. This is a reward the process. Semaphore 1, 0, 1, 2, 3, 4, etc. is the sad resource. A semaphore uses two atomic operations, wait and signal for process synchronization. The wait operation decrement the value of its arguments yes if it is positive. If yes is negative or zero, then no operation is performed. Next one, signal for the process synchronization. The signal operation increments the value of its argument yes. Next, semaphore usage. We can separate the 4 KB buffer into 4 buffers of 1 KB. Semaphore can be associated with these 4 buffers, allowing user and the producer to work on different buffers simultaneously. Next, advantage of semaphores. Semaphores allows more than one thread to access the critical section. Semaphores are machine independent. Semaphore are implemented in the machine independent code of the microkernel. They don't allow multiple processes to enter the critical section. As there is busy and waiting in semaphore, There is never wastage of process time and resources. They are machine independent, which should be running the machine independent code of the microkernel. They allow flexible management resources. Next one, monitor. The monitor is one of the ways to achieve process synchronizations. The monitor is supported by programming languages to achieve mutual exclusion between processes. For example, Java synchronized methods, Java provide wait and notify constructs. It is the collection of conditions, variables, and procedures combined together in a special kind of module or a package. The process running outside the monitor cannot access the internal variable of the monitor, but can call procedure of the monitor. Next one, the process running outside the monitor cannot access the internal variable of the monitor, but can call procedures of the monitor. Only one process at a time can execute code inside the monitor. Next, advantage of monitor. Monitors have the advantage of making parallel programming easier and less error prone than using techniques such as semaphore. Next one, dining philosopher solutions using monitor. Dining philosopher problem. Young philosophers seated around a circular table. Attention reader, don't stop learning now. Practice gate exam will before the actual exam with the subject wise and the overall quiz available in gate test series course. Crossover P1, P2, P3, P1, P5, nodes, nodeless. Listen. There is one chopstick between each philosopher. A philosopher must pick up its two nearest chopsticks in order to eat. A philosopher must pick up the first one chopsticks and then the second one, not both at once. We need an algorithm for allocating these limited resources like chopsticks among several processes like philosophers, such that solutions is free from deadlock and free from starvation. There exists some algorithm to solve dynamic philosopher problem, but they may have deadlock situations. Also, deadlock-free solutions is not a necessary situations free. Semaphores can result in deadlock due to programming errors. Monitors alone are not sufficiency to solve this. We need monitor with conditions variables. Next one, dynamic philosopher solutions using monitor. Uh, we illustrate monitor concepts by presenting deadlock-free solutions onto the dynamic philosopher problem. Monitoring is used to control access to state variable and conditions variables. It only tells when to enter and exit the segment. The solutions imposes the restrictions that a philosopher may be pick up chopsticks only if both of them are available. The code, the solutions we need to distinguish among three states in which we may find the philosopher. For this purpose, we introduce the following data source, thinking, country, and eating. Next topic will move to implementation of monitor using semaphores. Now, we consider a possible implementation of the monitor mechanism using semaphore. For each monitor, a semaphore matrix is provided. A process must execute wait before entering the monitor and must execute a signal after leaving the monitor. Since a signaling process must wait until the resumed process either leaves or waits, and additional semaphores next is introduced, initialized to 0, and the signaling process can use next suspend themselves. Now, because of an integer variable next count is also provided to count the number of processes suspended on next. Thus, each external functions f is replaced by weight matrix.